recombination, and to explain those results, we would have to have had a high power density, 75 watts per cubic centimeter, to measure the small excess heat that we saw. And that points out our results that the effect seems to be a volume effect as far as we could tell. We're not sure. It could be a surface effect, but I roughly figure you get about 1 watt per cubic centimeter of palladium. And that gives you an idea of what to expect for your experiments. If you go back to the MIT and Caltech studies, they had small volumes, and therefore you would not expect much more than about 70 milliwatts of excess power based on my results. And the question is whether their calorimetry was accurate enough to measure 70 milliwatts. But that would be what you would have expected, a small excess power. Okay. Now just two more slides of you guys. One is on helium. I just want to mention this. This is prepared by Ben Bush. He gave it at the poster at the American Chemical Society last week. But if you plot our NAWC, our name is now Naval Air Warfare Center, so we're now NAWC, but if you plot this versus energy, you have the 4 MeV line and 24 MeV line. You see that we do have some results that come close to explaining the helium that we see. And this is some SRI results measured by Ben Bush, but we are at least in the neighborhood or order of magnitude of what you would expect based on a fusion type reaction. What is the well, this just shows some other people who also reported helium-4. We've heard some of this today. Liao found it in the palladium. Bachris found some in the palladium. Yamaguchi, we know, in Japan. And these are some other people that are also in Russ George. And we'll be talking later this week about their results reporting helium-4. We don't know what the fusion reaction is. I just want to point out there are things besides DD fusion to consider. It could be lithium-6. It could be boron-10. I found this in a report to the Navy, Office of Naval Research contract. Had nothing to do with cold fusion, but they were proposing these reactions as reactions with no neutrons and reactions with no direct nuclear radiation for use on a submarine. And so there are other people who realize there could be other reactions that do not produce radiation or neutrons that are a possibility. And then just in conclusion, publications that we had in the past year, and I'll have some of these as a reprint out the poster session. Okay, thank you.
I think we have time for one question.
Yes. You were mentioning that Steve Jones has written a paper criticizing you. I mean, you gave him a challenge to write a paper, and he wrote it in September.
Right.
And this paper has many, many things that are very nasty.
Yeah, I know. I've seen it.
Why does the helium claim 10 times as big in 93 as in 91 for the same data?
The claim is 10 times as much?
Yes. I mean,
yeah.
On page 2, he has two tables, 91 and 93.
Okay. I hope I get a chance to write a rebuttal to his paper because that's easy to answer. When we first reported that, we did not know what our detection limit was. We did not have good data on our detection limit. We were reporting it as 0.1 part per billion at that time. But since then, we've measured the background of our system in metal flasks, and we know that in our background is around 4 parts per billion. So 0.1 part per billion could not have been our detection limit, because our background is 4 parts per billion. And so we know what our background is today. And so in the best labs that we go to, like in Amarillo, Texas, they can only measure it to plus or minus 1 part per billion. The University of Texas, just starting out new in this area, it's hard to believe that they were 10 times better than a major lab that does this all the time. So we were in error on our detection limit of 0.1 part per billion in our first paper.
I don't understand that. That's a constant amount. But you multiply everything by a factor of 10. 10 to the 12 becomes 10 to the 13th. Right. 10 to the 14th becomes 10 to the 15th.
Right.
It's a constant amount. You would not multiply every time by 10.
If your detection limit is 10 to the 13th, our background is 10 to the 13th. We know that now as a fact. So if our background is 10 to the 13th, then our lowest level that we could measure would have to be at least 10 to the 13th, right? Wouldn't it have to be at least that?
Yes.
Right. Okay, that's our lowest that we can measure. So, okay. So that is where we start.
I think in the interest of time, we should move on. I don't think there's a problem with this.
The battery's good. I think the battery's good. Yeah.
It remains only for Martin Flashman to ensure that we all regress most efficiently.
experiment is regressive, a notion which comes from the sociology of science, and I think that when the dust has settled, the sociology of the subject will probably be one of the most interesting aspects. Well, what do the sociologists of science say? This is really sort of a very quick paraphrase. They say, well, when something controversial starts, you don't know whether positive conclusions are correct and negative results are due to bad experimentation. And you don't, on the contrary, you don't know whether negative conclusions are correct and the positive results are due to bad experimentation. You really don't know that. Now, I think you have to look at this in a very flat sort of way. I don't think you want ever to use a word like skeptic and believer, because depending on which side of the fence you're on, you'll say one thing if you're a skeptic and another thing if you're a believer, but you've got to look at everything in a critical way. However, I think that we can go a little bit beyond the sociologists, because as scientists, I think you would say, well, let's look at it again, and let's ask whether key positive results was in fact negative, or a key negative conclusion are due to incorrect interpretations. It's really the questions, what do we say about the interpretation of a given set of data? Data are data, results are results, you know, those are just numbers. But what conclusions do we draw from those numbers? And I think that 6 years on, I hope that we could have perhaps rather more of this sort of debate at this meeting. Now, sociologists also tell us that the discovery is not made at a single point in time. I think we would agree with that. But again, as scientists, I think we might go further than that, and we might say that a set of questions isn't asked at a given point in time. Your questions adapt. Indeed, I think we can go even further than that and say that our interpretations are not completed at a given point in time. We have got different people who have a different bunch of data, different results, and we don't know whether the interpretation which was put on that given set of results was correct. And another point which I think is not understood, and this is really where I was aiming at this morning, is that our interpretations are subject to our knowledge of the system. If this morning I was showing you that this particular system has one nasty quirk to it, and that is that it sometimes shows positive feedback, and in fact it will only get energy out of the system at an appreciable level if you are in the region of positive feedback or past the region of positive feedback. So you are always in danger. If you think about operational amplifier circuits, you never calibrate them in a closed loop when you have positive feedback. You're really on a high to nothing if you do that. So we have to always ask ourselves, when we go back, is our interpretation sound? Because our knowledge of the system tells us that we may not have been all right. Well, I showed you this morning how you can get some idea of the presence or absence of positive feedback. And I thought I'd show you here a section of the Harvard data sets. Now, I think this has been shown before. Mike Mellish and Wolf Hansen showed this at the Nagoya meeting. I don't think it made very much impact. So this is not an original set. In fact, it's the Harvard data set. And here, what was very good about the Harvard design, I think the Harvard design, the design concept of the experiment was very good. These were cells 3 and cells 4 happen to have been in sodium hydroxide, sodium butyl oxide. And here is this seesaw effect, which Wolf Hansen was referring to, because of the changing level of the electrolyte. And here is the effect for D2O. And here's the calibration. Now, if you look at this, you say, well, something must be peculiar here. It doesn't take much to see that something is really very odd. Because the behavior of the H2O cell is really exactly as you would expect. The behavior of the D2O cell is strange. First of all, if you look at the calibration and you try and put a line through here, you'll see that as you put the calibration, there's only one heat calibration pulse in these two cells, which is consistent with the heat calibration which we use. The temperature rises and it goes down, and this line here continues. If you look at the heater calibration applied to the D2O cell, you see it does not relax back. So you'd say immediately, there must be a problem here. Incidentally, it didn't, of course, it didn't come to equilibrium. It didn't come to a quasi-steady state when taking off. So you'd say, well, probably there's some positive feedback. Let's ignore that. You can see that the D2O cell shows these excursions in temperature. Now, the thermodynamic systems don't show excursions in temperature unless there's a source of heat. They're either not sound, either the experimental device is not sound, or else we must say that there's a source of heat. Now, I think Wolf Hansen's done a splendid job on it, and he tells us that, well, this thing is correctly around 1% or so these excursions in heat really must be significant. Well, let's carry on with that. There are lots of these, just for this particular cell, there are lots of these excursions. They're scattered about, I don't know, 27, 30 excursions in temperature. We can look at it in somewhat more detail. Here is the measurement for the H2O cell. So we can do our standard trick on this cell. We can say, let's not assume anything about it. Let's just look at the lower bound heat transfer coefficient for that cell. That's what that tells us. I think I want to use that again. And if we have the D2O cell, notice incidentally this continuation up here. We do the D2O cell, we see it doesn't relax. First of all, it's flat here. There's no change in temperature which you would expect it to take place, and this doesn't relax. So you'd say, well, that must, if there's positive feedback, if they actually managed to drive this cell into positive feedback, then they would have had a big problem in calibrating it. Well, let's reduce just that single day. I'd say that our approach, I will point out to you that we have a different approach to analyzing data to that which Wolf Hansen was talking about. We like to analyze things day by day. We like to look at each little bit in here. So let's look at the lower bound heat transfer coefficient for this particular piece here, which is got a calibration on. And we find that the heat transfer coefficient changes with time. This is really a reflection of the sort of tidal effect which Wolf Hansen was mentioning. There's nothing untoward, unduly untoward in applying the heater calibration. It doesn't allow for the heater power in, the heater power off. We get this decrease. We get quite a substantial, about 15% decrease. That's very important to get 15% decrease. Now that's about what we would expect for this cell. Wolf has already shown you. This is our cell, our recent version of the cells we've used since October 89. With silvering at the top to remove the tidal effect as far as we can. And this morning I showed you can really keep the heat transfer coefficient constant to 1 part in 1,000. But in the Harvard cell, which had all this glass on the top, and there was no silvering, of course we expected to see a change in the heat transfer coefficient with time. And that's what we do. You see this change in the heat transfer coefficient with time, this decrease. Well, what do we see if we look at the D2O cell? We see that the heat transfer coefficient does not change markedly with time. Now, according to the scheme I gave you this morning, if you've got a heat transfer coefficient and it increases with time, that must mean that you are losing some sort of exothermicity. So the logical interpretation of this, the difference between these two, is that in the heavy water cell, there was a source of excess entropy here, but this decreased with time, so consequently this expected decrease is slewed up. Well, you might say that's pretty tentative, so you have to really look for other ways of investigating that cell. One possible strategy which you can adopt is to say, well, okay, fix on one particular point to evaluate the heat transfer coefficient. And these minima are very convenient. In the H2O, in the Harvard study, they added warm H2O, or warm D2O. So you always got a cooling curve here. This is very useful, incidentally, this cooling curve. So you can say, well, let's look at the heat transfer coefficient here. Now let's take the tidal effect into account. And this will cause this decrease in the heat transfer coefficient, which I pointed out to you. And let's make a thermal balance day by day as we go along for the cell. And it works pretty well. We see that here is a thermal balance, 0. This is 200 plus 200 milliwatts, minus 200 milliwatts. These were 6 millimeter diameter electrodes and 1 centimeter long, made of highly pure metal, sintered metal, whereas ours were not so pure and made of cast metal. And we see that eventually these cells become slightly endothermic, and that means we have overestimated the change of the heat transfer coefficient with time. But that's okay, because we're going to have a look at the D2O cell, and it's better to overestimate. It's better to go on the side of making something negative. If you're looking for an effect which should make something positive, it's better to go on the side of making it negative. So let's just have a look at what happens when we look at the D2O cell. So what we're going to do, just back up again, we're going to look at these, see what the thermal balance tells us along here. And it's really no very big surprise that we will get some excess energy, some excess enthalpy, and we do, whenever we have an excursion, we have an excess enthalpy. But of course, using this particular data processing strategy, we can only get the excess enthalpy with respect to a set 0 here. There may not be a 0 here. Each time we repeat this process, we set to 0. So we get about maximum about 200 milliwatts excess heat, excess enthalpy, and this goes on and on throughout the cycle of the order of 200 milliwatts, which is about the same as Stanley Pons and I had in 1989 at the comparable current density. So the question is, what does all this mean? Well, what can we conclude from this? I think we could say the calorimeter works correctly and excess enthalpy generation was observed. Or we can say the calorimeter does not work correctly. We can say nothing about it. I think what we cannot conclude is that the calorimeter works correctly and that there's no excess of generation excess energy. That's not a logical conclusion. Now, I think we should look at this. I don't want anybody to go away and say, yeah, who sucks? It is always possible that the calorimeter did not work correctly. I think the only thing we can really say at this point is we cannot draw this particular conclusion. We can draw one of these two, but not that. And just to finish off, I will just say two things. How are we doing? Oh, plenty of time. I'll say two things, footnotes to this. The first point is I think that it's greatly to the credit of the group at Harvard that they made these data available for further study. I think there's an object lesson to us in that we made our data available for further study. The world, in fact, insisted that our data should be studied independently when we were working in the university sector. And it's greatly to the credit of the group at Harvard that they did do so. And I'd also say that going back, really this is a question of the sociology of science, which I think we should take seriously. That data analysis is not completed at a given point in time, and that one's view of a given set of results does change with time, and it changes according to what we know about the system. And the process of data evaluation is usually curtailed And the reason why it is curtailed, of course, is partly because the costs are so high. I think that if you do a realistic costing on data analysis, you will find in your what you've done in the past, we have all been guilty of truncating data analysis. That the costs of data analysis are frequently much higher than the costs of gathering the data. And there is no, really, one of the things which is very bad about modern science is there is no means of funding the re-examination of key experimental data. And then what often happens is they're just lost. So you can't do anything. So what you have in the end is conclusions and not the basis of the conclusions. So I think that we have a developing subject and we should take, I would recommend that we take these thoughts to heart. Thank you.
Is there a question? We have time for one question.
Bye.
Do the data sets, of which you have an enormous number, get revisited for the purpose of making clear what's working and not working? One of the things that strikes me after listening to both Ed and Mike today is that we have a major set of variables that are not pinned down. We have, obviously, this general class called the proper material and the selection of the proper material. It seems to me that the argument that you make could be much stronger for reviewing and analyzing old data sets if you were to look at them as basically filters on an enormous variety of different samples of data.
Thank you for that. I think, can I just, you may want to say something more than that, but I think there is a lesson here which I forgot to put across. And that is that we have these bursts. We have bursts as well. But we think that this is especially severe if you use sintered material. Now the reason Harvard used sintered material, there's David Thompson here. David, are you here? It's very simple that when they ordered their material from Johnson Matthey, David was out of the country. So they got sintered material, whereas everybody else got cast material. Is that permissible to say that, David?
Yes.
Yeah, it's permissible to say that. Okay.
Oh, well, actually used where you need to be using the sintered material in that particular.
So there is an interesting lesson here. It's worthwhile revisiting the Harvard data set to see what sintered material looks like. And in fact, there's a lesson for us that we really have to have a bigger database for sintered material.
Well, the point I'm making is that for those of you who have data sets, who run experiments, and you've had success or not had success, you happen to be sitting upon a lot of information which is pertinent to the selection of the appropriate material. That is not available within the normal publishing limitations that you find in most journals. It is certainly our experience, upon looking at the Harwell data, that we were able to go from an estimate of 15-20% uncertainty in their calorimetry well down into the 4.32% inaccuracy level. And that was sufficient for us to be able to look at interesting things, or lack of interesting things, if you will, in the material. That I believe may be generally true. And given the paucity of support for this area, I would argue that to have a look at your results in terms of a set of parameters which at this time we think are appropriate, and decide whether or not your materials that you did those old experiments on gave us any information, would be a useful contribution. It flies in the face of the normal publication that if you haven't done your work this year, it's not worth publishing anymore.
I know it's you'll be interested to know that I'm recalculating a lot of our 1992 data sets. I really want to know exactly what we did in 1992 with some further knowledge. And I think one has to do that. Unfortunately, I think that especially academic scientists are under such pressure that this just doesn't get done.
which is very
I
sad.
think we should leave it there to be fair to the final two speakers today. That concludes the XSCQ calorimetry session. We now move on to the session on nuclear measurements. Is Dr. Mengery here? Is that good? One of the previous speakers broke the clip on this microphone. Who has the clip for this microphone? I think it came off when the last person to trip over it.
I've seen the label of somebody.
Yeah, Melvin, do you have the clip to this microphone in your lapel? You do, thank you.
Yes.
Well, one of the main problems with the detection of neutrons from a weak source is to have a low or a great signal to background ratio. So for this reason, this is a quite trivial observation, but just for this observation, some people was hiding several thousand feet underground to look for to decrease the background. I have a lot of admiration for this paper. Anyway, there is another solution for people who is not enough in love for cold fusion or not in hate for cold fusion to afford such hiding underground. And the method is to use another system of detection, which is to measure the time of flight of a neutron between two scintillator spectrometers. I will give you some principles of the instrument. When a neutron is impinging the first detector, we will call the scattering detector with energy AN, the neutron will be scattered to the second detector with N1 energy. And clearly there is a loss of energy which depends from the angle of scattering. The time of flight between the first and the second detector is given from the ratio of the distance of the path of flight to the velocity, which we can obtain strictly from the energy A1. There is a problem anyway. We need to have the first detector of a small size, otherwise we will have multiple scattering. And on the other side, to have enough sensitivity, we need for the second detector a large angle to collect most of the neutrons which are scattered. And this problem poses another problem, which is that we have a larger range of angles, and so a larger determination about the energy, because from the time of flight we need to measure the energy of the neutron which was impinging the first detector. Well, I am just presenting the solution which was found out by my friend Claudio Manducchi. If the first detector is a geometrical point and the second detector is just a surface, a spherical surface in the front of the first detector, it can be shown that the time of flight of the neutron depends only from its original energy as independent from the scattering angle. We will see through some geometrical consideration and kinematics this statement. This represents, we are now on the coordinate of a laboratory. This V1 is the vector of the neutron impinging the first detector. V2 is the proton in the scintillator. After the collision, clearly, we have a change of energy, the conservation of the total energy, and we have this situation. If we are now going from the coordinate of the laboratory to coordinate measured with respect to the center of mass of the system, we will have that the velocity of center of mass is half the velocity V1. Since the proton and neutrons have more or less the same mass, we have also this equation. And so if we are coming back from the coordinate of a center of mass to the coordinate of the laboratory, we can do this construction. For this triangle, we can apply the Carnot theorem. And we have all this data. And we will arrive that V1, we have how to calculate V1 from the original data which are obtained through the equation.
Take a step to the right. You're blocking me.
I see. Okay. Anyway, we are arriving through geometrical consideration of the Carnot theorem to this situation. And here again, we are taking out the root, and we are to this situation that the time of flight is independent from on the path. So is a constant, which is the basis of the instrument. We will now consider some details about the construction of the instrument. The construction was requiring a compromise between the manufacturing of the instrument and the performance of the instrument. Practically, the most critical point was the construction of the second detector, of the hemispherical detector, which is represented by this shell. This is a shell of AE1024 plastic scintillator, which was collecting the radiation scattered from the first one, the scattered detector. The scattered detector was instead a liquid scintillator for N-gamma separation through pulse shape discrimination. Both the detectors are seen by phototubes. The first one, phototube, is separated to have a cleaner signal from the first detector. The second one instead is connected through a pipeline to the detector. To have a first evaluation of the performance, the instrument was calibrated, and the calibration was made in two ways: by a Monte Carlo simulation and by using monoenergetic radiation from the laboratory of Legnaro using the proton-lithium nuclear reaction. For the comparison of the simulated and real signals, we have first of all compared the spectrum achieved on the firmer detector, on the scattering detector, the liquid scintillator detector, with the calculated. And you see the points represent Monte Carlo simulation, and the continuum lines represent the real spectrum. And there is a nice fitting, which means that the program, the Monte Carlo simulation, was good, and the answer of the scintillator liquid spectrometer was all right. But what was important for us was to have the measure, to have the answer about the time of flight of the spectrometer. And this is reproduced here. The continuous line here represents the simulation. The broader line represents the real spectrum in time of flight. We see that there is some broadening of the monoenergetic, the answer of the spectrometer to monoenergetic neutrons. Anyway, this broadening is clearly due to the fact that the spectrometer is not built from a geometrical point, the first detector, and from a surface for the stopover detector, but they have a definite size. Anyway, we see that there is a rather good fitting between the peaks of simulated and the real spectra, especially if you are going towards energy higher than 1 MeV, 1.5 MeV. Another method for calibration was made by comparing the spectrum of a Californium source with the time of flight spectrum obtained by the spectrometer. Here, the continuous line represents the Maxwell distribution of Californium, which was computed on the basis of a temperature of 0.85 MeV. And this is the real distribution in time of flight, which was found from the source, the real source. The same thing has been made also for the scintillator spectrometer, the starter detector, or the scattering detector. Here we have the proton recoil energy spectrum compared with the theoretical Monte Carlo analysis. We will now consider also what was eventually the result of this calibration. This was made through electronics, and so we were in position to achieve a correlation between the time of flight of the neutrons and the energy of the neutrons. The value of 40 MeV is rather approximate. As a further step of the evaluation of the instrument, we measured the background. And this is the answer of the instrument to the cosmic background. The background was measured this way. We have reported, in function of the time, the energy, the number of counts, the integral number of counts, divided in each energy range, which I have shown before. First thing which I note is that neutron of highest energy represents the prevailing part of the spectrum. Neutrons of energy below 1.5 MeV are not reported since they represent only 5% of the entire spectrum. Other points to be noted about the background are summarized here. The neutron background is reduced with respect to the rate of a source lined up with the spectrometer. This is what I have said in my introduction. A method to reduce the background is just to have a time of flight, because the answer of the instrument is only for the neutrons which are scattered by the first detector with momentum towards the second detector. And so if I have a source which is lined up with the instrument, the signal of the source will be exalted with respect to the background. And in the meantime, just because I am monitoring neutrons from a source lined up with the instrument, I can say, yes, neutrons are coming from that source. I don't know if I am clear enough, but this is another test of the possibility that neutrons are coming out from the source. The background measured by this instrument has lower fluctuation than the background seen by usual scintillation spectrometers. In fact, with scintillation spectrometry, we generally observe in the low energy range a sharp increase of the signal, because all the neutrons, all the signal are accumulating towards the low energy part of the spectrum, noise, and so on. And last but not least, we see that the background in the range of 2.5, 1.5 neutrons is particularly low. So if we are looking for the DD reaction, we have a window particularly clean of background. The first thing which was made was to compare the energy of the background measured by the instrument with what we were able to find about the energy of the cosmic background. The average energy measured by the instrument resulted to be 13.2 MeV. To have the average energy of the neutron background, we used this equation, which was supplied by Rossi some more than 10 years ago, which is giving, this function is giving the differential intensity of neutrons in the vertical direction of the depth 6. Practically, the radiation of the cosmic events is increasing as we are moving to the top and decreasing as we are going down. This is clear. If we are staying in a fixed position, this equation is transformed in this more simpler form. If this equation is integrated among the limit of our instrument, which were 0.45 MeV to 40 MeV, we calculate the average energy. The result is 16.3 MeV, which is fair enough compared with 13.2 MeV computed measured, not computed, by our instrument. As a last part of this presentation, we are just going towards the cold fusion, that is measuring, using this instrument to measure neutrons from a deuteride sample. Well, here I am showing two experimental designs which were used for loading deuterium inside a palladium sample and giving furthermore a stimulation, an electric stimulation to induce the emission of neutrons. According to the first design, the palladium sample, which was a disk, was piled inside two copper discs, which were used as electrode. On the bottom, the contact between the sample of palladium and the electrode of copper was made through a thin ring of gold. The scope, the aim of this design was to minimize the surface of contact between gold and palladium, so to have a larger current density at the surface of contact, and so to have possibly some gradient of electric potential inside the sample. This was a hope. Probably this was not the better design, because the length in which we have a gradient is surely small. Anyway, the system was working, because now we think that when 1 ampere or 2 ampere were crossing the sample, probably at the contact you have a discharge of deuterium, and so you are creating inside the sample a gradient due more than migration to diffusion from the discharge of deuterium. The other design instead was made in a way that the palladium sample was contacting one electrode and was separated from the other by an insulator, a mica disc. So to this second copper disc, an high potential could be applied. We have used this design because it was found that when a palladium sample is submitted to an high field, we have a phenomenon which preliminarily we are calling field-induced overloading, whereby we observe really an increase of the loading ratio. Okay, shall we go to the results? Here I am plotting the integral counts, net counts, that is, counts clean from the background. If we could compare with the background, we see that these counts represent about 70% increase over the background. We see another point, that the answer in the 4 energy range is totally different. For instance, A4, which represents the energy of DD reaction, is now probably one of the most prevailing emission in the spectrum. So we observe also that the net emission is no longer clean, smooth as the background, in that it can alternate some constant period, which means no emission, with some sharp period of sharp emission. And another point, the emissions are not time correlated at between. The same experiment was performed with the stimulation of electric field. This was electric current, this is electric field. Here we have still more than in the other experiment, alternated time in which the sample is quenching for some type of emission, and times in which we have a sharp emission. This sharp emission was monitored also by another scintillation spectrometer. And in fact, when we have a sharp change of slope of the integral plots, we have surely an high emission. And this was indeed seen by the second spectrometer. Well, the experiments which I have shortly described were repeated for 8 experiments, and for each one we are reporting the energy, the net neutron emission in the 4 energy, the total emission, and the increase in counts with respect to the background, and eventually the total increase of the emission with respect to the total emission of the background. We see that the increase is 0.75, 0.6, and 0.70, and so on, which means that in average we had an increase of 70% of the emission with respect to the background. This is clean emission. Last, I will show an histogram in which we are showing this histogram is showing what was the percent of any emission with respect to the total of the emission. If we are considering the emission at about 55 MeV, which could fit with the emission with DD reaction, we see that this represents not more than 20% of all the emission. If you are comparing this emission with the background, anyway, we see that the emission corresponding to DD reaction was representing an increase of the background of about 160%. I've finished. Thank you for your attention.
Time for one question, yes.
In case the sample emits bursts of neutrons more than one at a time, does your analysis take this into consideration?
I must say one thing, that we have been looking for neutrons for 5 years, and I cannot say that from this type of experiment we never saw significant neutron bursts.
Okay, just one last question.
Please let me know the size of your detector. Size.
The size? I have forgotten. Yes. I have forgotten before. The second detector has a diameter. I have shown the sphere. The diameter of the sphere is 10 centimeters, which was a compromise, between manufacturer having enough.
The first.
Scattering detector. The first.
No. The distance between the first detector and the shell is 10 centimeters. This is the longest flight path.
How is the first detector?
How long is the first?
How long? The first detector is 100 cubic centimeters.
One last question.
What's the efficiency?
The efficiency is 5 for 10 at minus 5. No, 3 for 10 at minus 5. Anyway, we have the poster. There is Claudio Manducchi who had the idea of the instrument and is the magician of the subject. He will be very happy to give you all the type of answers.
Thank you
okay?
very much. We have Dr. Stella to give a presentation today. Thank you very much.
tu? Upgrade of Fermi apparatus with detection and identification of charged hadrons in the few MeV energy region, and a cryogenic loading of palladium up to 1.33. Apparently these two topics have nothing to do with each other, but you will see they are strongly correlated. Charged hadrons means protons and light nuclei. Few MeV means more than one MeV. And this is a group from Italy, Rome, Frascati, which is not far from Gran Sasso, so it's less difficult to be underground. What is the Fermi detector? It's a high efficiency, low background neutron and gamma detector for cold fusion experiments. It's by now published in Nuclear Instruments because it's a nuclear instrument. Yeah? In Nuclear Instruments and Methods, just the last number 1 month ago. And you see that the nuclear instrument, which is mostly against cold fusion, for the first time has published something which is named cold fusion experiments. Okay, this is a comprehensive nuclear particle detector aimed to have multiple correlations, which is achieved by this upgrading I'm talking about, to answer the general question if cold fusion is a nuclear phenomenon, and possibly which nuclear reaction do participate in this phenomenon. So in order to answer this question, we need the identification of the nuclear products, the energy measurement of several types of products, and for instance, you need to possibly detect protons together with tritium, and not only alone. Alone we did already, and we found some tritium excess. So the Fermi detector, as you find in this paper, is a complex system of neutron detectors. These are 2 meters long, so it's a quite big detector with helium-3 and a distribution of plastic thicknesses different from detector to detector to allow the measurement of the average energy of the neutrons. And it is at Gran Sasso underground laboratory. Already it was possible to observe with this detector neutrons with high efficiency, not 10 to the minus 4, but 25%. Very low background, gamma rays with high efficiency, low background, tritium offline, and now we aim to measure protons and light nuclei in the few MeV energy range. Fermi has a lot of virtues. I cannot list all of them, but mostly high neutron efficiencies, very large efficiencies, and low background, multi-hit fissure, and so on and so. 10. Now we want to add the 11th one, protons, and with these features, we think it's the best possible neutron detector. Nuclear detector, sorry, not neutron, nuclear detector. We have already, it's going out in fusion technology, a paper on the excess of neutrons stimulated by thermal neutrons. So how to detect the charged particles? We have a threefold detector with 2 proportional chambers and a cesium iodide scintillator in order to have a triple coincidence and to have the E over dx measurement and energy measurement. The structure of the detector, of the charged particle detector, is this one. These are the wire chambers. This is the cesium iodide with phototube. There is a window for calibration with alpha particles. And then you need the charged particles. How do you produce a charged particle? So you need a thin sheet here, thin palladium sheet. There is some collimator here in order to have straight going charged particles. And with collimator, the efficiency is of the order of 2%. The acceptance, the acceptance is of the order of 2%. You need a special electrolytic cell in order to have electrolysis on one side and wire chambers on the other side. And I cannot go into details of this, but it is designed, positively designed for this scope. For instance, with alpha particles from americium source, you get plots like this one, where the two pole sides of the two wire chambers are summed here, and this is d over dx measurement, and here you have the cesium iodide pole side, which measures residual energy, and there is a negative correlation, because if you lose much energy before, you cannot lose it later on. So this negative correlation is useful. After energy calibration, this distribution looks like this one, with alpha particles. And here you see the KV energy of the alpha particles and the energy released in the wire chambers. The detector is well understood, and there is a good comparison between Monte Carlo simulation and data for the cesium iodide pole site here. You can achieve a good energy resolution because you have this first wire chamber, second wire chamber, cesium iodide, and if you sum it in the appropriate way, you get a very narrow pole site with very good resolution. And these are data. But we want to measure protons. How do we get protons for calibration? So we have a window which is made of mylar in front of the alpha particle, and we get the protons from Rutherford scattering from the alpha particles on the mylar window. And this is now the lower part of this pole site. The alpha from the source are far away here. This is how it does look like before correction for pressure and temperature effects. This is background, noise, electronic noise mostly. These are probably cosmic rays here, and these are the protons as coming from mylar before correction, and after correction you get a nice narrow d over dx curve with noise out here and energy calibration here due to protons. You might compare it with the expectation for energy loss, and it goes correctly with the expectation. And the protons from scattering on mylar have a endpoint of 3.44 MeV, which is close to the 3 MeV we would like to detect in case of fusion. Actually, the observed energy, of course, you don't observe the dead material, the loss in the dead material. The observed energy is close to 3 MeV, and it's very narrow. So in this way, you might expect something which in average looks like this one. Protons from mylar are the red ones here at 45 degrees, And from palladium, since they will be at 90 degrees, they will be separated and different in this way. Between green arrives to the end point of the expected protons from 1 MeV to 3 MeV above. But in this way, we could expect to detect light nuclei, and this is the average expectation for light nuclei. For instance, alpha particles at 90 degrees, not the source ones, which are power, from 3 MeV to 5 MeV, helium-3, tritium, deuterium, of course, protons. And protons now are much lower because the scale has been compressed. Unfortunately, when the palladium is loaded, the deuterium could go out toward the wire chamber, and then it would disprove the wire chamber pulse height. So this is the average pulse height for alpha particles, and this is time. And so if you have a naked palladium on the side of the wire chamber, it will get out some deuterium, and then the loading will be worse. So we have tried to put something to coat this side, and with some 5 microns silver, we had something constant here. But when the loading achieves 2/3, silver breaks and cracks, so this is not enough to reach high loading. So we can, in principle, observe many things, but due to this problem, cracks, the loading will never be very high, so we need to find another solution for very high loading, and I will show it. And the potentialities of this upgraded detector are very good because we can detect neutrons with measurement of average energy, gammas with energy, tritium, protons with energy and identification, and so on, alpha particles, and light nuclei, thermal effects. Also, we can control the deuterium concentration, and all these features allow multiple correlations, time correlation and energy correlation. So now, how to overcome this problem of the loading? We went back to a paper from Semiletov et al. In Moscow. Yes. In '88, which claimed to have achieved 1.33 loading, and we have tried to reproduce it together with Dr. Odier from Kazan, just on February '95, with 2 different procedures. The first procedure has not perfect results. What is achieved is PD3H4 in a tetrahedral structure, but it's a mixed state with also beta phase. Not only this will be gamma phase tetrahedra, but it's mixed, and with diffraction, you wouldn't see the diffraction rings, but some confused pattern because it's at the same time gamma phase and beta phase. With the second procedure, which is this one, outgassing, and then a few minutes into hydrogen, and then fast cooling with liquid nitrogen, you achieve gamma phase, very pure one, I will show it, and this is exactly 1.33 ratio because it's this hydride. By electron diffraction, we know this, and also by Fourier analysis and by other methods, the diffraction gives you a pattern, very nice, pure pattern. This is a bad transparency, but the original one is much cleaner, which shows clean tetrahedral rings corresponding to the tetrahedral structure and pure 1.33 ratio, which is measured also in other ways. Now, if you heat up this sample after having produced, by the way, the vacancies are quite small, not well known, but less than 10%. If you heat up this state, you get another phase. Here it's called a gamma prime phase, where the parameter is only one, the crystal parameter, which is 2.995 angstrom, because this is a cubic structure now, and it is very stable at normal condition. How do we know that this is cubic? Because the diffraction pattern is very clean now, and the ratio between the rings is what is expected for a cubic structure by Fourier analysis. And there are no vacancies, and this phase is stable after many was the same phase which was found in 1988, and it is stable for a long time. If you heat up not at 650 degrees, but 850 degrees, then you get the composition of palladium and hydrogen in a separate phase. So we have both gamma and gamma prime phases are stable at normal conditions, even 8 years stability with this incredible ratio. The samples have been carefully investigated by electron diffraction. Unfortunately, this is not possible for thick samples. This is possible only for very thin ones, 100 angstrom only. Otherwise, you need neutron diffraction, and this has not been done yet. And also, thick samples have not been produced. With the second procedure, pure gamma phase has been obtained. Actually, not exactly hydrogen was used, but ammonia. And what we will do as next will be to use deuterium to achieve this compound, hoping to get the same features. At the end, since these samples are very thin, I repeat, 100 angstrom, we will use these heavy loaded samples as thin films to detect not only protons, but light nuclei. So now you see the correlation between thickness and proton detection, heavy loading and proton detection, and nuclear detection. To conclude, we have realized a comprehensive nuclear detector with multiple correlations possible. We have got thin sheets of hydrogen over palladium 1.33 loading, and we will try deuterium over palladium as well. And in this way, systematic nuclear measurements are or will be made possible. Thank you.
Thank you. Are there any questions? Yes.
This guy reported a similar structure in September. In this physical review letter, he reported, I believe it was your PD3D4 structure. He identified the superlattice. Is that the same structure? Are you familiar with Fukai's paper?
No. Fukai, no, but I'll explain. I don't know if this is
Very recently, he reported a phase, which is a effective palladium lattice with a nominal composition P3H4.
Yes, he had a void.
The main body.
there has been no investigation if this is a molecular state, a real molecular state, or just a crystal structure. For that, you would need Raman spectra and so on. No?
It was an ordered phase. He had done diffraction. It was, I believe, September 20th, physical review letter. So I'll give you the record.
Yeah, we'll be sure to make sure you get that reference number.
What did you mean when they used 0% vacancies or what?
Vacancies less than 10%, but we are asked. If you assume that the system is pure without vacancies, you get a good fit of the results. And if you assume some random vacancies, you can also get small vacancies, you can also get a good result.
Vacancy is what, though?
We'll use sub-levels of vacancies in
Empty sites, yeah?
Empty interstitial.
This is not a mass spectrometer.
Maximum energy of your gamma spectroscopy.
Gamma spectroscopy. Well, this is 8 centimeter crystal. It's quite high. It's many MeV.
Several MeV?
Several, yes. 23 will be possible. It's not C. Not.
At most 7 MeV
Of course.
I just want to point.
Some experiments on the variation of tritium radioactivity of tritium absorbed by petting. Please, Doctor. Right slide. Somewhere. Okay.
Good. Does it work? Yes. Thank you. Ladies and gentlemen, to tell you that this is not a lecture, it is an experiment, because it is 20 years ago that I have given my last lecture. I hope it will be a successful experiment, and what you will know that not all experiments are successful. In a recent letter, I have given a description of an evaluation of experiments where tritium was incorporated in small titanium particles and where sharp decrease of the radioactivity was observed. In this lecture, I will give a more detailed description of these experiments and evaluation and of further experiments. By this procedure, a very high degree of evidence for the strange effect of the decrease of the radioactivity of tritium is obtained. The outline of my presentation. In the introduction, I will give the historical background, and part of it is a preparation of the small titanium particles. Then I will describe two heating experiments, one with a lower concentration of the tritium in the titanium, and the other with a 10 times higher concentration. With this experiment, during the whole increase of temperature, the tritium remains in the preparation. And we observe a sharp decrease of the radioactive decay constant of tritium. In this experiment, the tritium leaves the preparation during heating, but again, a sharp decrease of the radioactivity is observed. Then I will describe experiments which I have indicated STETX experiments. From this experiment, a nuclear pair hypothesis is derived. The concluding remarks will deal with the bearing on cold DD fusion. Something is wrong. Yeah. Does it work? Yes. At first you may allow me.
It's still here. In any case, you can. That's right.
At first you may allow me a few words about the strange and sometimes funny history of this work. It was in the 1960s. I worked in the Philips Research Laboratories in Eindhoven on field of neutron generator tubes. During this work, I discovered for myself, it was of course discovered several years ago by other people, the preparation of small metal particles by evaporation of the metal in an inert atmosphere. Here you see electron micrograph of a preparation which I have made by vaporization of titanium in argon of 1 centimeter of mercury pressure. You see small titanium particles about 10 nanometers or 50 nanometers in diameter. These are monocrystalline particles. They are arranged in chains with many ramifications. In this manner, one gets a very loose, sooty deposit, which is very absorptive for the uptake of hydrogen isotopes. At this time, there was a technological problem with gas discharge tubes. If one applies the voltage on the tube, there is a time lag between the application of the voltage and the ignition of the discharge. To reduce this time lag, a small amount of radioactive material is applied in the tube at a suitable place. Our titanium preparation, where we have absorbed some tritium, was very suitable for this purpose. However, there is a problem with temperature stability because the tubes have to be baked out at elevated temperatures of about 400 degrees centigrade. Therefore, we had to investigate the temperature stability of these preparations. At that time, I was very busy with my neutron tube work. I therefore asked for a student who could assist me in the work on temperature stability. The student came, the work was done, the report was prepared, and it was we would like to give this report to the professor that my student could get his degree. The work was done, but the professor did not accept it. And my student had to do other work. When it regards the historical report, I must say that I will do the work today in another way. The report is like a field with many stones and mud, but under the dirt, some very especially valuable jewels were hidden. Our professor did not see them. After my retirement, I digged in the mud, and I found some of these jewels, and I should like to show you some of them. After some preliminary experiments, where we have painted our preparation to small nickel sheets, and we have heated these in a vacuum and measured the radioactivity before and after heat treatment. But this was not easy. It was a long time taking procedure. We thought about a better method to measure the temperature stability. This can be done with two ways. One method is to increase the temperature of the preparation in a vacuum tube and to measure the pressure rise of the tritium pressure. We have made here a titanium preparation, 48 milligrams. 48 milligrams titanium, 100 millicurie tritium. This is a preparation. The atomic ratio is 1 tritium atom to 300 titanium atoms. And during increase of temperature, we measured the pressure of the tritium, which was released. In this sheet, we see the results. Graph B shows the increase of tritium pressure at the first rise of temperature. And graph C shows it at the second rise of temperature. With the first rise of temperature, the tritium pressure does not increase below about 350 degrees centigrade. And with the second rise of temperature, the increase of tritium pressure occurred very much earlier at 250 degrees centigrade. We explain this difference in the following way. The small titanium particles are covered on the surface with a thin oxide layer, which prevents the tritium atoms released from their bonds to the titanium lattice, that they can release the small titanium particles. The preparation was heated at the first rise of temperature up to 480 degrees centigrade. And when the temperature was high, the oxygen atoms diffuse into the bulk of the titanium particles, that clean surface is obtained. A clean surface of the titanium particles is obtained. Then, at the second rise of temperature, the tritium atoms which are released from their bonds to the titanium lattice can immediately leave the small titanium particles. This conclusion, which is very important, has to be ascertained by further experiments applying ultra-high vacuum technique and definitely determine oxide layers on the surface of the titanium particles. But from this conclusion, we can say that the second increase of pressure shows us the release of the tritium atoms from the titanium lattice. Another means to measure directly the release of the tritium from the preparation is a measurement of the radioactivity in the preparation as a function of the temperature. We use this arrangement. The preparation is made in this tube, the same preparation with the same atomic ratio as with the first experiment. A thin steel window at the lower end of the tube and two aluminium sheets, two aluminium foils at the bottom of the oven. The tube is placed in an oven, allows a definite part of the X radiation which is generated by the beta particles of the decay of tritium to leave the arrangement and to be measured by a GM tube. Today I would use beryllium for the windows and the solid state detector for detecting the X-rays. Graph A gives the count rate as a function of temperature. It is very strange that at a temperature of 150 degrees centigrade, the radioactivity decreases sharply and reaches at 160 degrees centigrade 72% of the initial value, followed by a slower decrease and reaching 60% of the initial value at 275 degrees centigrade, and then it increases to the initial value, reaching 360 degrees centigrade before the decomposition of the preparation. We see also the decomposition of the preparation with the increase of temperature with the first experiment. The sharp decrease of radioactivity between 150 degrees centigrade and 275 degrees centigrade cannot be explained by a release of the tritium from the preparation. This is clearly shown up by this graph, which shows that under 350 degrees centigrade there is no serious release of tritium. This conclusion is ascertained by many experiments with technological applications. But the strongest argument that no tritium is released in this temperature region is the fact that the radioactivity increases again to the initial value. And this shows definitely that no tritium is lost in this temperature region between 150 degrees centigrade and 275 degrees centigrade. Therefore, we come to the following preliminary conclusion. In the temperature region between 150 degrees centigrade and 275 degrees centigrade, a new tritium compound, I call it a preliminary as a compound, is formed in our preparation with a lower radioactive decay constant, and upon further increase of temperature and before decomposition of the preparation, this lower emitting compound is destroyed. The increase of the radioactivity just started at the same temperature as the increase of pressure at the second rise of temperature. We arrived to the preliminary conclusion that this is the temperature where the tritium atoms lose their bonds to the titanium lattice. From this coincidence, we arrive to the preliminary conclusion that the binding of the tritium atoms to the titanium lattice is a necessary condition for the decrease of lambda. Then we made an experiment with a 10 times higher concentration. We used 2 tubes of a similar design than with the first experiment, but with a lower heat capacity. The heat capacity of the first tube was very high, and therefore the experiment took a long time. We took about 10 hours for the total experiment, and this experiment was done about 5 times faster. In tube S, we made a preparation of 40-80 milligrams in both tubes. We made the preparation of the finely divided titanium of 48 milligrams. And in tube S, we absorbed 1 pyritritium in the titanium preparation. This tube was placed in an oven, and during heating, the tritium, which released from the preparation in the tube S, was absorbed by the titanium preparation in tube G. Therefore, we measure with this GM tube, we measure the gas which is released during heating from this preparation. Here's the result. The count rate in tube S, which means solid, is constant up to 210 degrees centigrade, and then it increases steeply. At the same time, the increase of the count rate in tube G, which means gas, increases. This may lead to the preliminary conclusion that all the tritium which is released from tube S is absorbed by tube G. To a more complete evaluation of this experiment, we arrive we arrive to normalize the count rate of tube G to the same sensitivity as the count rate of tube S. Thus, the count rate G gives us the amount of tritium which is released from the preparation, and S plus G is a measure of the total radioactivity. We see a similar decrease and re-increase of the radioactivity as in the first experiment. It is very important that this experiment is done under a very different condition with a different, a decreasing concentration of our preparation, and the concentration at the minimum of the radioactivity at 275 degrees centigrade is 8.5 times higher than with the first experiment. It can be shown that the cause of these two experiments is equivalent. With first experiment, the tritium atoms which regain normal radioactivity remain in the preparation. They cannot leave it on account of surface contamination. And with a second experiment, the tritium atoms which release their bonds to the titanium lattice leave the preparation, but the total radioactivity has the same course than with the first experiment. The only difference is that here the tritium atoms remain in the preparation, and with this experiment they leave the preparation. Here I have an experiment with a concentration which was nearly 2 times as high as with the second experiment, where the tritium leaves the preparation. And you see that we have also a decrease and a re-increase of the radioactivity. It is not so high, it is only 9%. But this preparation was exposed to ambient air a few hours, and then a titanium layer was oxidized about 40 angstroms on the surface of the titanium particles. But what is very interesting that in these experiments, the tritium atoms which regain normal radioactivity remain in the preparation. By our heating experiments, we arrived to the conclusion that a new compound of the tritium with a decreased radioactive decay constant is formed in our preparations. However, there is no physical effect known which accomplishes the observed decrease of radioactivity. We have speculated that the decrease of the radioactivity may have something to do with the different phases in the titanium tritium system, a suspicion which has not been confirmed till now. Therefore, experiments were undertaken to measure the radioactivity as a function of the concentration of such systems. The concentration was taken as independent variable X, and the relating experiments are therefore indicated as TETX experiments. It would be very interesting to do such experiments at different temperatures, but up till now only TETX experiments at room temperature has been done. All TETX experiments are made in this arrangement. The titanium preparation was deposited on a gold electrode. We used very thin titanium layers of about 25 nanometers. Then a cylindrical electrode was lowered into the bulb, and small amount of tritiums were added successively. And the emission current was measured by a vibrating reed. The increase of the emission current was measured by a vibrating reed electrometer. Here is the result of this experiment. Okay? 5 minutes. Yeah. We see the increase of current decreased to about 55% at 3 times 10 to the power minus 4 equal, and then it increases again to the initial value. From this and further TETX experiments, a nuclear pair hypothesis was derived which reads explicitly: 2 tritium nuclei under certain conditions, in our case by embedding in small particles of titanium, arrange themselves in a pair with nuclear spin 0. Such a nuclear pair acts for the decay to a certain extent as a parent nucleus, so that the radioactive decay changes to a certain extent into a higher forbidden one. I should like to emphasize that the nuclear pair hypothesis is a hypothesis. This implies that it is the first attempt to explain the strange effect of the decrease of the radioactivity. It is to be proved or disproved by further experiments. Furthermore, nothing has yet been said about the nature of the hypothetical nuclear pairs. It would, for instance, possible that we have pairs where 4 tritons are implied in a tetraedrical configuration. There is a strange suspicion that the 2 different effects, the cold DD fusion and the decrease of tritium radioactivity, are caused by the same or a related fundamental principle. Hydrogen isotopes, deuterium or tritium, are sorbed in suitable metals, and nuclear properties are changed in a quite ununderstandable manner. The fact that sometimes cold fusion experiments with a positive result are not reproducible points to the existence of a hidden necessary condition, of more hidden necessary conditions. For the effect of lambda decrease of tritium, such a condition may be monocrystallinity, or another may be smallness of the metal particles. Both can be investigated experimentally. It may be interesting that in the experiment of Martin Fleischmann and Stanley Pons, published about 2 years ago, where excess enthalpy reduction was observed with deuterium absorbed in palladium, analogous conditions for the formation of small palladium hydride particles are present as for the formation of our monocrystalline titanium particles. Increasing the concentration of deuterium above the end of the alpha phase, one gets supersaturation of the alpha phase, which results in homogeneous nucleation. This brings about formation of small monocrystalline particles of palladium hydride. To get homogeneous nucleation, the palladium metal has to be very poor, a condition which is also necessary for the production of excess enthalpy as reported by Fleischmann and Pons. Otherwise, one gets inhomogeneous nucleation with the formation of bigger and non-monocrystalline hydride particles. It is suggested that the microstructure and possible monocrystallinity of the palladium hydride suspended in the palladium matrix should be investigated by metallographic techniques at different states of saturation. With both effects, cold diffusion and decrease of tritium radioactivity, identical particles interact. The cold diffusion gives the possibility to check if such interactions are only possible between identical particles. This may be indicated as homo interactions, or also between non-identical particles, indicated as hetero interactions. If one gets neutron production in a cold fusion experiment, the DD reaction, by DD reaction, one has to repeat the experiment with a mixture of 50% deuterium and 50% tritium. If the reaction occurs between non-identical particles, one has then to observe a high intensity of 14 MeV neutrons from the DT reaction. The result of such an experiment is very important for the theoretical interpretation of the cold fusion effect. If the reaction happens only between identical particles, I think many theories would be ruled out. I thank you very much for your attention.
Thank you. Yes. Thank you for the interesting report. We have time for a few questions.
I would only like to make a comment because I think the situation is very, the system is a complicated one, and especially this is a question of possible new phases of titanium hydride at different temperature, and the possible effect of oxygen on the surface. So it's quite complicated. But one conclusion can be taken already at this time, and that is a general conceptual conclusion. That is the very fact that weak interaction physics, which is sensitive to energies of the order of GeVs, never mind, is just modified by just being inside the lattice, just brings the paradigm of bonding and all that, or condensed matter, totally to a falsification. And the reason is simple. The lattice in the present paradigm, in the present solid-state physics, can only exert actions at the level of electron volts, can only exchange energies at the level of the electron volts. And here we are essentially talking about GeV. Never mind that the electrons has a spectrum with the 18 keV endpoint. But the physics of the weak interaction is that order. So you have several orders of magnitude difference. So, this is just underlines something I would say today in my lecture, that never mind, forget about bonding, non-bonding, and so on and so forth. This is you're clearly talking, the only way of understanding this is to bring collective interaction, namely the whole of the whole particle interacts with the single tritium, decaying tritium. And this is not unheard of. The Mössbauer effect is another example of this. So, the theorists are advised, and well advised, not to I mean, to just give up the usual explanations. This is a real new physics. This is we are entering a new phase in our conceptualization of the interaction within condensed matter.
Well, this was a comment, and I think we have just time for a short question.
Take notice.
Very short.
Well, very interesting.
You know that we can rationalize GED.
Very interesting observation, but for the
If you can pick
no, for the benefit of the skeptics, I would just like to like you to assure that since what you are measuring in the experiment is a current, if there are some surface coatings on the titanium that is formed, and since the range of beta particles is hardly 1 micron, I am sure you have looked at it and made sure that nothing gets deposited which brings down the current. That's the only question that one has to make sure. Thank you.
Current, you mean?
The current, what he is measuring, the radioactivity is measured through the vibrating rate electrometer. So essentially the quantity he measures is a current. And if there is some phenomenon which brings down the beta range, I'm sure you have looked at it.
Yeah, but the micron, he has nanometer.
No, but if some oxygen or something.
Yeah, but
I know, that's
well, I mean, but this is a particle of a nano, of 20.
No, not the particle, something else.
Yeah, but I mean, he has a micron over hundreds of a micron.
So what I have measured in the heating experiments is the X radiation which is generated by the beta electrons. This is a schematic picture of our preparation. About 80 titanium particles. About 80 titanium particles are piled up in the preparation, and there was an objection in a Zeitschrift für Naturforschung recently that the cause of the radioactivity is can be explained that the tritium is in beginning.
Fast, please.
Yeah, that the tritium is in beginning adsorbed at the surface, and then it goes to the bulk when the radioactivity decreases, and it goes again back when it re-increases. But this cannot explain the cause of higher radioactivity, because we have here not one particle, we have about 80 particles. And the beta electrons are completely decelerated in our preparation. Therefore, the X radiation is a good measure for the beta radioactivity.
Okay, thank you very much again.
So how can you have a one line?
Now we pass on to tritium and go to neutrons. And we listen to
Alpha phase. I have forgotten to say. Always alpha phase.
Okay. But you may have different concentrations.
Anomalous effects and continuing the form crystals upon the ferroelectric.
Very much. Ladies and gentlemen, I'd like to say about anomalous heat effects in DKDP crystals upon the phase transition through Curie point. Earlier we have detected the generation of products of nuclear DD fusion, neutrons and tritium in DKDP single crystals on the phase transition through Curie point. There were found essential asymmetry of neutrons and tritium yield such that 10 to -7. This asymmetry cannot be explained by accelerating mechanism of d ions. On the other hand, there are strong non-equilibrium conditions realized upon the phase transition through Curie point, in which the giant fluctuation of domain wall elastic energy density could be occurred. This giant fluctuation are the analogies of multi-phonon coherent excitation. There have been proposed that to ferroelectric phase transition, the coherent model of Hagelstein could be applied to this transition. Then in crystalline lattice of DKDP, in addition to the process leading to the generation of neutrons and tritium, there might occur the coherent transfer of virtual neutron from deuterium nuclear to the neighboring acceptor nuclear. In such a case, on the phase transition through Curie point, the transitional thermal parameters might undergo certain changes due to appearance of an additional source of heat in DKDP lattice. For the purpose of studying an additional heat release on a ferroelectric phase transition in DKDP crystals, we have investigated the kinetics of the thermal effects and its quantitative changes on the phase transition in vicinity of Curie point. We have used a Mettler microcalorimeter with constant rates of cooling and heating as 4.8 kelvins per minute and 0.5 kelvins per minute. Samples was a single DKDP crystals with mass 50 milligrams with deuterium content 97%, cut out from one single block oriented in the 001 direction, and similar to them KDP crystals with the mass 605 multiplied 9 minus 2, as well as control samples. In the DKDP crystal containing 97% of deuterium, we have kinetics of heat effect is there. This is kinetic of heat effect in DKDP crystals with deuterium concentration 97%. The curve 1 is second temperature cycles, and the curve 2 is 82nd temperature cycles. The curve 3 is kinetics for crystals with deuterium concentration 70%. It has any shift in low temperature region because it is isotopic effect. We can to measure the delta H values that it can be the value of transition heat. In the case of KDP crystals at substantially smaller delta H values than those of the KDP crystals, at any number of thermal cycles we have delta H exa more than delta H enda effect. An increase in the number of thermal cycles up to the 18 leads only to an insignificant narrowing of thermal peaks by about 5% and to some decrease narrowing of thermal peaks. Thus, the experiments show that single crystals of KDP structure, both containing deuterium and lacunite, demonstrate completely different behaviors of the phase transition heat on thermal cycling in the vicinity of Curie point. It is the table in which you can see